Hello, my name is Wenhui Tang. I'll be talking about my research project about the collective curvature sensing and fluidity in three-dimensional multicellular systems. So most biological systems have naturally curved surface, for example, intestine, alveoli, and embryo. And understanding the cell migration behavior on those curved surface can help us understand a lot of biological processes, such as the morphogenesis, bone healing, as well as the tumor metastasis. However, it's currently not clear whether those substrate curvature can play a role in regulating the cellular behavior. So here, we would like to ask a very simple question: can cells sense curvature and how curvature affects cell behavior? We use two systems with multicellular scale curvatures to study the effect of curvature. We first grew MDCK cells onto PDMS wells with different diameters, and then we use a more physiological long alveolar system derived by human-induced pluripotent stem cells. Both of them have spherical surface, which can represent different curvatures. We then track the cell position with time, and we are able to get the cell velocity field. And our result shows that the cell sense multicellular curvature in a collective manner. And interestingly, we found that the cell velocity is not affected by curvature. However, as the substrate curvature increases, the cells reduce their collectiveness, and the multicellular profile becomes more dynamic as we calculate that divergence, curl, and shear. The curvature-dependent behavior is very exciting, and we would like to understanding why. And we find that the hexagon cells tend to form clusters on different curvatures, and by overlaying the hexagon patterns with the divergence and shear field, we find that the high divergence shear always occur outside or at the boundary of hexagon clusters. And this suggests that the hexagons are more solid-like, while the non-hexagons are more fluid-like. And we then write the proposed energy model, which includes the free energy difference and the elastic linear energy difference. From this equation, we can derive the critical hexagon pack size, which linearly increases with the sphere radius r. And this is what exactly we observe in our experimental systems. And I'm also interested in some directions includes the collective dynamics in 3D intestinal organoids and the topology of cell pachyons spheres. I would like to acknowledge my advisors and collaborators and also the funding resources. And thanks for your listening.